Thanks very much for this very nice introduction. I can try to upload it. I can try to do it myself, or I'll try. I can destroy. No, but they upload it here. It's supposed to be somewhere here. Okay, thanks again for this not very well-deserved introduction. This is kind of a weird talk. I think in this kind of popular talks, it's impossible to satisfy everybody, obviously, because there are people with various backgrounds in the audience, but I think that this particular talk will stand out by not satisfying anybody rather than everybody. For those who know something, there will be nothing new, and for those who don't know anything, it will be completely impossible to understand. So, but let me proceed nevertheless. Am I supposed to take questions or no? Okay, so maybe at the end, if somebody has some. Okay, yeah. So if there are any questions, then do stop me. Yeah. So this is some. I don't have a pointer, but maybe I don't need one. So this is some attempt to try to explain some motivations for some of the work that is happening in our field. It's not necessarily too much around my own work. It's just a general introduction to how I see certain things that are developing. And there will be lots of things that you know, maybe a tiny bit of things that are new, but yeah. So I just wanted to start from something extremely basic and go from there. So the question in this talk is going to be about the limits of fundamental theory. That's the theme of this talk. So we're going to try to discuss the limits of fundamental theories. And I wanted to start with an example, which is that you could imagine this kind of thought experiment that you lived 200 years ago, and you, with all the knowledge that you possess now, and somebody tells you that there is this universal law of gravitation, and you're supposed to answer the question of whether you could, just by pure thought, understood back then that this cannot be exact, right? I mean, that this cannot be ultimately correct. I mean, it's obvious that it's approximately correct, but your goal was to try to understand if it can be exactly correct. And so, first of all, when you see this equation, it raises a few philosophical questions, right? I mean, the equation seems to posit the existence of point particles. And the question is, does it really posit the existence of point-like particles? So, and the second thing is that this equation obviously implies that there is infinite speed of information transmission, since once you move a mass that is anywhere in space, it would instantly affect masses that are anywhere else in space. So maybe that there is something wrong with that. So, and maybe there is also nothing wrong with imagining that there are no point-like particles, and this equation should always be interpreted as applying for mass distributions. So the point is that one is led to all sorts of difficulties if one tries to really understand if this equation could have been exact. So for example, if you ask what is the energy that is stored in a gravitationally bound system of mass m and radius r, then the answer is something like gm squared over r. That's the energy. And this is kind of disturbing. So why don't these balls of energy of mass collapse? Because you can obviously decrease the energy if they just collapse. So you could ask, okay, so if we really assume that there are no fundamental particles and everything is just a mass distribution, then where are all these infinitely small remnants which would be obtained by collapsing? And of course, now we know the answer that, well, general relativity does not allow for like an infinite collapse in some way because there is an event horizon. But this equation does not lead to any sort of event horizon. So you could ask, why doesn't it lead to infinitely small remnant particles that are all over the place? So where are all these supermassive remnants? Or you could say, okay, so maybe this equation does imply that there are fundamental point-like particles, and we have to live with that. But actually, 200 years ago, people didn't know, but now they know. There was a recent development on this subject in 1992. You could ask if the Newton equation actually makes sense, if it's well posed for point-like particles, and the answer is no. So it turns out, and which this was proven only in 1992, and it's not completely well understood yet, but it was shown that there are solutions to this equation in which a particle shoots off at infinite speed, at finite time. So this equation has singularities which are very similar to the singularities that appear in Navier-Stokes equations, which are not fundamental equations, and therefore this cannot be a fundamental equation either. So these singularities appear even if there are no collisions. And then you could have a discussion of maybe it's okay that there are such singularities because maybe they only appear for extremely fine-tuned initial conditions. But again, remember that there are no collisions in these solutions. And secondly, it's not presently known that these singularities appear only for infinitely fine-tuned or measure zero set of initial conditions. So in short, the equation leads to nonsensical solutions for point-like particles. And if you try to get away with only having mass distributions and never point-like particles, then you are led to various difficulties because you are left with this problem of where are all these remnants, which are point-like. So you could be dissatisfied with this equation and you could think, okay, so maybe it's not a fundamental law and it has to be ultimately revised. So in light of these very lowbrow comments about this stuff, I just wanted to start like some discussion about what is the exact realm of applicability of modern theories of fundamental forces and particles. So are they complete? Can they be complete? And what is the state of the art in particle physics and as well as gravity? So for the sake of the discussion, I will assume that quantum mechanics and special relativity are correct, meaning that they're exact. And that means that the fundamental theory of whatever probably does not look like a lattice of spins, and that does violate Lorentz invariance and rotational symmetry very brutally, and it would have been observed generically. So theories of fundamental forces and particles, if they are to be exact, they have to start their life from some kind of lattice model in which you can take the distances between nearby spins to essentially zero. That's the only way to recover rotational symmetry and Lorentz invariance. But it's not clear that such limits even exist. So most of the time when we study quantum field theory and particle physics, we don't talk about this limit where the distances have been taken to exactly zero, which may not exist. We're talking about some theories that do have some kind of lattice structure, and we're discussing the physics at energies much below the scale in which you could see this lattice structure. So that's the terminology that I'm going to use. I'm going to try to distinguish between effective theories, which are theories like Newton's law in some sense, right? That they are valid only in some regime, in energy scale or distance scale. They're not exactly valid, and they're not mathematically even self-consistent at any energy scale or at any distance scale. They predict various infinities, like Newton's law. And by contrast, there will be complete theories. Complete theories are theories in which you could mathematically at least, self-consistently, use that theory to make predictions about any set of initial conditions at any energy. But the question is whether in the state of the art of theoretical physics is that we have complete theories versus effective theories. Effective theories are not mathematically self-consistent and they're inconsistent ultimately, while complete theories are completely mathematically self-consistent. Now, I sort of keep jumping between these effective theories breaking down at short distances and these effective theories breaking down at high energies. And that's due to the uncertainty principle. The uncertainty principle in quantum mechanics relates short distances and high energies. So when I talk about effective theories, you can equivalently either think about them as predicting their own demise or their inconsistency at the high energy scales or alternatively at short distance scales. So our effective theories will be valid for some energies which are below the cutoff scale. So E cutoff is going to appear in various slides, and that will denote the energy scale above which the theory predicts nonsense. Or alternatively, you could think about some cutoff in distance, which is a cutoff from below. And by contrast, a complete theory does not need any sort of cutoff. It can be extended to any initial conditions with any energy. So it's actually extremely not obvious that complete theories exist. You're asking if there is a set of equations that suffers from no such singularities for any set of initial conditions and does not have any limitations on the initial conditions, meaning no limitations on energy scales or distance scales. And for a long time, as you know, in the Landau school in the 50s, people didn't even believe that there are such theories, which are completely well-defined mathematically and rigorously and have no limitations on their initial conditions. But of course, now we know from the 70s that there are plenty of such theories, which are called non-abelian gauge theories in 3+1 dimensions. Now, by we know, I mean physicists know, but mathematicians have not yet accepted this piece of knowledge. I mean, it has not been embedded in proper mathematics. So we physicists think that these theories are completely well-defined and do not need any cutoff, and they can be really defined in the continuum with no limitations on any initial conditions. But it's up for grabs in the mathematics community to try to show that this is true. So again, and by contrast, effective theories are not entirely self-consistent. And for some scattering processes, some initial wave packets, some initial conditions, you would get just nonsensical answers, similar to these infinities that appeared in solutions to the Newton equations. So now comes the interesting part. So far it's just terminology of what I mean when I say effective, what I mean when I say complete. The interesting part is when you try to ask whether effective theories can be completed. And this is the crucial point which I'm going to hammer out for the rest of this talk. So suppose you start with some set of mathematical rules that don't apply above some energy scale. So they only apply for energy scales which are smaller than the cutoff scale, and they only apply for, like, say, initial conditions with small energies. There is a well-defined question whether we can modify the theory, which is effective, in such a way that it would not change the predictions that this theory makes for low enough energy initial conditions, but it would allow to raise the cutoff scale to infinity. So an effective theory can be said to be completable if that procedure can be carried out, namely whether we can deform the theory, but by not changing what it predicts for low energies, but changing what it predicts at high energies, and in particular raising the cutoff all the way to infinity. So such theories would be particularly nice because we could just complete them to infinity and we could think about them as fundamental theories that do not need any restrictions. And a crucial point that I'm going to try to make is that it's important to ask whether the modifications that you need to do in order to achieve that are mild or kind of brutal. So one way in which you could imagine doing such modifications is to add finitely many particles, and we'll see some examples of that. So suppose you could just add some finitely many degrees of freedom at the cutoff scale, and from that point on, you could raise the cutoff to infinity. And on the other hand, it could be that there is no way to do that, and the only way to raise the cutoff to infinity is by adding infinitely many particles. And that would be kind of, so this is the distinction that I'm going to draw between different effective theories. So let's start with some examples from the history. So Yukawa's theory for pion interactions. So Yukawa gave this phenomenological model for neutron-proton interactions via pion exchange. And the pion is a massive particles that mediate some kind of Yukawa potential between the neutron and the proton. But it was, I think, very well known, but maybe somebody who knows the history better can correct me, that this cannot be ultimately correct, because that theory clearly doesn't make sense for a neutron-proton scattering above 1 GeV. One is led to all sorts of divergences and nonsensical results. So this is an example of an effective theory which applies perfectly for nuclear physics, but at low enough energies, which are less than 1 GeV, giga electron volt. So this is an example of a model that is mathematically fine for some set of initial conditions, but not for all of them. And similarly, there is Fermi's theory for beta decay that allows to start from a neutron and let it decay to a proton and some neutrino and antineutrino and electron. And in that theory, again, it was, I think, obvious already back in the 30s or 40s that this effective model cannot be completely correct It only makes sensible predictions for energies which are lower than 100 GeV. So let's discuss the two examples. In both cases, somehow, historically, we've been extremely lucky. It turns out that in both cases, you can raise the cutoff to infinity by adding only finitely many particles. Just finitely many particles. In the first case, this is achieved by quantum chromodynamics. Quantum chromodynamics replaces this crude model with a completely well-defined, mathematically consistent model at all energy scales. And in the second case, it's even easier. You don't even need strong interactions like in quantum chromodynamics. You can explain the beta decay by the exchange of W bosons. And once you introduce W bosons and the famous Higgs particle, the theory becomes completely well-defined at any energy scale, essentially. So we've been extremely lucky in both cases, because in both cases, we could raise the cutoff all the way to infinity to make the theory complete by a rather mild modification of the theory, just adding a few particles. Now, as I said, one case is kind of hard to see and one case is easy to see, but that would not be important. I'm just trying to make a conceptual distinction between when it's possible with finitely many particles versus when it's impossible with finitely many particles. So let's now discuss the standard model of particle physics. I'm going very fast, but it's okay. So in the standard model of particle physics, in which I'm going to neglect gravitational interactions for the moment, we can ask, is it a complete or an effective theory? It's a legitimate question to ask about, the fundamental theory of nature. And the answer is the following. The answer is that it's ridiculously effective, in the sense that the cutoff is so high, it's a 10 to the 45 GeV. The cutoff is so high that it doesn't matter for any practical purpose, because nobody is going to prepare initial conditions with energies above 10 to the 45 GeV. And as you will see in a second, when we turn to discussing gravity, this number is completely obviated. It's kind of physically completely irrelevant. So the theory is strictly speaking, only effective, but the cutoff is so high that it's of no practical consequence. And furthermore, it's very well known that this cutoff can be easily pushed to infinity by what's called grand unification, which is a weak coupling construction, or even electric magnetic duality, which is a strong coupling construction. So the standard model is like in the best of shapes. The cutoff is already extremely high, and if you are a purist and you really want to push that cutoff all the way to infinity, it's trivial to do. We know how to do it both at weak coupling and at strong coupling, and there is nothing more to add about it. So the standard model is in great shape from this point of view. But gravity, which we've so far neglected, really brings a lot of trouble to this story. So I want to discuss the famous fact that gravity is incompatible with quantum mechanics, which is false. But I want to try to explain in what sense it might be true. So if we just start with the Einstein-Hilbert action, which is the general relativity essentially, we encounter a cutoff at the Planck scale, which is a very high scale, but it's still much lower than that scale that we've seen before. So there is a cutoff at what's called the Planck scale. And let's see how this comes about. Suppose you want to compute the gravitational force between two distant masses. So there is this formula that I put here for the force between two distant particles, and you recognize that the first term is the famous term discovered by Newton, and then there is some correction due to general relativity, no quantum mechanics, and then there is a correction due to quantum mechanics, which has an h bar. So this last piece is the most important piece. And as you can see, if the distance between these two particles is short enough, is small enough, then this term can dominate over the first term, because it goes like 1 over the distance squared. And any term that we would further compute in some kind of perturbation theory in h bar would be ever more important at short distances. So we see that this is why gravity has a cutoff at the Planck scale. We cannot do sensible computations for the force between two particles at distance less than the Planck distance, which is something like 10 to the minus 35 meters. So we cannot do sensible computations below some distance scale, or equivalently, we cannot do sensible computations for some scattering processes of wave packets, because there is this kind of divergent series, and it makes no sensible predictions. But that's okay. I mean, the same would be true for proton-neutron interactions. You would encounter very similar issues. So what's the real difference between gravity and and just Pion physics, or gravity and the beta decay processes, I mean, they both look extremely similar from that point of view. They lead to some kind of nonsensical results for some particular set of initial conditions. So people often say that it's hard to unify gravity with the standard model, but that's kind of meaningless, because you can unify them up to the Planck scale and it makes perfectly sensible predictions. It's only if you try to go beyond the Planck scale that you encounter difficulties. And here I want to come to the most important point that I wanted to make, which is that there is a difference between Pion physics or W boson exchange and gravity, even though they are both, like, they seem to lead to the same sort of nonsensical predictions. There is a fundamental difference. It seems that with gravity, it's impossible to do it to complete the theory with finitely many particles. So nobody has ever been able to add the finitely many degrees of freedom to the standard model plus gravity and ameliorate this kind of singularities that occur at very short distances. It has been so far impossible. But we know that it can be done with infinitely many particles. That is what string theory has achieved. That it's a construction with infinitely many new particles in which these short distance singularities are ameliorated. So this is a fundamental difference. And in string theory, the cutoff is raised by indeed introducing infinitely many particles that sit on linear edge trajectories. And so such a relation between masses and spins that appears in string theory is also approximately true for ordinary quantum field theories with finitely many degrees of freedom, such as quantum chromodynamics. But in string theory, it's presumably exactly true that m squared is j, while in quantum field theory, in ordinary quantum field theories, it cannot be exactly true. It can only be approximately true. This is something that would be very nice to prove. It can be made into a mathematically well-defined statement, but it has not been possible to prove so far. Okay, so there are also many people who still believe that you can ameliorate the problems with gravity at short distances by adding just finitely many particles. There are whole communities doing that, like the asymptotic safety kind of thing, and loop quantum gravity, and many other communities, but none of this has been so far successful. It appears that there is a fundamental obstruction to completing gravity all the way to infinite energy scales with finitely many degrees of freedom. So the fact that gravity is non-renormalizable, that people often say, is a complete non-issue. It's an irrelevant thing to say, and no pun intended here. It's a completely irrelevant thing, because there are many other non-renormalizable theories, and we're not scared of them. We can complete them with finitely many particles. And also the fact that gravity appears to be about geometry seems to be completely irrelevant to me. And also the fact that gravity has something to do with Einstein, while quantum mechanics has something to do with Dirac and Heisenberg, and this also seems completely irrelevant. That like two different groups invented these two theories. And the central actual difference, if you want to pinpoint it, if you want to really point on the central difference between gravity and all the other theories, effective theories that we've seen before, it's very hard to pinpoint it. But in my opinion, it seems that gravity cannot be fixed by introducing finitely many degrees of freedom. That seems to me to be the crucial issue. And we have extremely strong indirect evidence for what I'm saying. There are many other bizarre and tantalizing properties about gravity, such as the holographic principle, the entropy of black holes. And these kind of things are extremely closely related to what I was just saying about having to introduce infinitely many particles. Because if you look, for example, at the only successful attempt at reconciling the black hole entropy with ordinary physics, this is the counting of the entropy by Strominger and Waffa. And that relies crucially on the infinitely many fluctuations in string theory, infinitely many new particles that string theory introduces. So in the only setup in which we were able to completely understand the holographic nature of gravity, meaning the entropy of black holes, it required very, very strongly that there would be infinitely many kind of particles and solitons to account for the entropy. So the various tantalizing or bizarre properties of gravity that people keep flaunting, such as holography, the black hole entropy, the information puzzle, and all these things, this, in my view, are extremely closely related to having infinitely many particles. At least in situations where we can compute, it's been extremely important that there are infinitely many particles. Otherwise, it would be impossible to account for the entropy of black holes. So we see that some complete physical there are some apparently mathematically completely self-consistent theories that do not need any cutoff, so they can be defined for any initial conditions or any energy scale. And while mathematicians have not yet recognized this fact, it seems to be true. And also there are lots of effective theories that are almost as good, meaning that they can be fixed, and we can make them into completely mathematically well-defined models by just fiddling a little bit with the particle content at the cutoff scale. But gravity seems to be different, and while I was trying to pinpoint the difference, it appears to me that while it's hard to say it rigorously, it appears to me that the difference is that you can't really fix gravity in any easy way. You can't just invent a new Higgs mechanism or something of that sort that would just fix it. And presently, we only know of just one way of fixing this disease with gravity, and that is what string theory has done, namely to introduce infinitely many new excitations. And I was going very fast, but I guess that's fine. So thank you all for the attention. I guess if there is any question, I can try to answer it. If there is any question or comment of what I was saying, maybe I was saying something wrong. Yeah. Right. Yes. By quantum mechanics, I did not mean Schrödinger equation. By quantum mechanics, I meant that there is an operator, which is that there is a Hilbert space, and there is a unitary operator that allows you to move forward in time. That's what I mean by quantum mechanics. That the space of states is a Hilbert space or a Fock space, and that the motion in time is implemented by a unitary operator on this space. I do not mean the Schrödinger equation with some particular, but yeah. And these two things, just saying that there is a Hilbert space and that there is a unitary operator, are not in contradiction with special relativity. Now, if you take these two properties and you try to add special relativity into the mix, what you discover is this thing that I try to explain, which is complete quantum field theories, like quantum field theories that are valid for any set of initial conditions. It's like a lattice model in which you could shrink the distances to 0 and you would still get something reasonable. Any other comments or questions? Yeah. Right. So, right. Yeah, obviously it's a great question. I try to add one. So, let me just say it in the way I understand it. So you could ask. Let me just answer it technically, not like kind of qualitatively. Technically, what I mean is that if you take M Planck to be very large, and you require that. In weakly coupled theories, what you do is you add new particles which parametrically below the cutoff. So the Higgs particle, is parametrically below the cutoff of the standard model without the Higgs particle. The cutoff is like at 1 TeV, but the Higgs particle is 100 GeV. So suppose you wanted to fix gravity by adding particles at parametrically smaller masses than the cutoff. This is impossible with finitely many particles. That's what I mean technically. And while if you try to venture out of these kind of restrictions, this is the same as saying that the tree-level scattering amplitudes, if you just allow for tree-level exchange, cannot be fixed with finitely many particles, unlike in the standard model, in which you can fix it with just finitely many new particles. Now, you could try to ask if you can fix it with finitely many degrees of freedom at the Planck scale. I have no idea how. That's what many people are trying to do. Loop quantum gravity, asymptotic safety. They have not been successful. The only thing I know, which everybody knows, is that if you try to raise the cutoff with weakly coupled particles, you cannot do it with finitely many weakly coupled particles. And this is in contradistinction with many other effective theories. It's hard to say, in my opinion, something beyond that at this point. Any other questions? Okay, so thanks again.